So now, as I mentioned at the end of the previous video, thanks to the existence of such a Weyl differential omega, we can rewrite this Ag equals in terms of this one. And here, H is determined by the divisor of such a Weyl differential minus G minus D. And in order to see that they are essentially the same, first let me observe that in this case, this definition makes sense. So that means the support of D and the support of H is disjoint, because if we take the valuation of the divisor H, which can be written as a sum of these valuations, and since D and G has a disjoint support, this valuation is going to be 0, and since D contains Pi, this is going to be 1, and thanks to our assumption, this is going to be minus 1, so this is 0. So that means support of H does not contain any these given distinct places Pi's. So that means the definition of such a code makes sense. And again, as I explained in the previous video, by the duality theorem, we know the existence of an isomorphism between these two vector spaces, and this isomorphism is explicitly described by mapping a function x to Weyl differential x omega. And we know that the Ag code, which is derived from these Weyl differentials, and an Ag code which is derived from in terms of the evaluations of the functions from this Riemann space, will be in one-to-one correspondence. So the any code verse, also any coordinates of the code verse will be also one-to-one correspondence. More explicitly, for a function in this Riemann space, we know that local components of the Weyl differential x omega is Pi of 1. And by the definition of multiplication, we know that this is Vpi of x. And since omega and x satisfies desired properties, we know that this local component can be written as evaluation of the function x at Pi and the local component of omega at Pi of 1. And by the assumption, this is 1. And this gives us x of Pi. So that means indeed these two structures contains the same n-tuples with the same coordinates. And this gives us the equality. So as a summary, we know that these Ag codes are related to each other in terms of the dual relation, thanks to the existence of such a Weyl differential omega. And indeed, thanks to this picture for instance, if we just, and mainly, even in the exercises which can be supported by the segment, in general, we will be interested in these constructions and how we can write explicitly this, such a canonical divisor. But before then, that we may give some conclusions thanks to this equality. For instance, we can conclude that a code is self-orthogonal or self-dual by only checking these divisors G and H. More explicitly, if this canonical divisor omega, which satisfies these properties, if this H is bigger than or equal to G, we can conclude that this AG code is self-orthogonal, so it lies in its dual. And in case of we have equality here, this code is self-dual. Because we know that the dual of an AG code can be written in terms of AG code with this divisor. And if we have this equality, so that means the Riemann-Roch space of this divisor lies in the Riemann-Roch space of this divisor, can be seen as a subspace. And thanks to the equivalence of the Riemann-Roch spaces and the AG codes, we can conclude this inclusion. And similarly, the equality gives us the characterization for the self-duality. And in the last week, one of your homework question will be to conclude using this, again, the previous proposition. So this, thanks again, using this equality. And by using the parameters or the estimation for the parameters of these three structures, indeed, we can estimate the parameters of an AG code in terms of the parameters of an AG code, which is described in terms of Weyl differentials. And your second homework, again, thanks to this equality, indeed, we can conclude that for the equivalent divisors, again, we get equivalent codes. Here by the equivalence, we mean the code equivalence. And conversely, if we have a linear code, which is equivalent to AG code C omega D of G, then we can see the existence of a divisor G prime, which is equivalent to G, which is disjoint support from the support of D, and indeed This can be also described in terms of NH equals C omega D of G prime. And in last two lectures, indeed, we want to understand this setting. So this, particularly this description, when we consider the AG codes which are derived from the rational function fields, because our final goal will be to understand the structure of BCH and the Gopukos in more details.